Hello, good morning students. I hope everybody is doing good. Today we are going to study the topic transformer, the last part of the chapter alternating current. In this topic we are going to study the principle of the transformer, then construction of the transformer, equations of the transformer, and last losses in the transformer. So before going in this topic, we are going to study the interactions part of the transformer. Yes, why do you require a transformer? What is the role of the transformer in transmission line? So here, as per these equations, Pc is equal to I square, or Pc is the waste of power in the transmission line. This is the transmission lines, and these lines are hundreds of kilometers long, and we know that resistance is directly proportional to the length of the conductors. If length is more, resistance is also more. So this distance is more, therefore I square R loss is also more, and that is what waste of power in the connecting cables. Yes. So in transmission line, this Pc waste of power is of no use. So here we have to minimize this waste of power. This is Pc. So as per these equations, Pc is inversely proportional to the V square here. What is V? V is the system voltage or a transmission voltage. Yes. At generating stations, generating voltage is 11,000 volts. As the length of this cable goes on increasing, we have to increase the voltage to minimize the waste of power in the cable. And this equation is given in NCERT book 3.35 in the current electricity chapter. Yes. So to minimize this Pc waste of power in the system, we have to increase the voltage. Means this voltage we have to increase. As the distance goes on increase, we have to also increase the voltage. Yes. 11,000, 22,000, 33,000 and so on. On the other hand, our residential, commercials or industrial connections are powered with this voltage, single phase 230 volts and three phase 415 volts. Again, this voltage is not safe to use the electricity. So what we have to do? We have to decrease the voltage from this high level to the lower level. So it is necessary to change an alternating voltage from one to another of greater or smaller value, and this is done with a device called the transformer. So for this purpose, to minimize the waste of power into the transmission line, we have to increase the voltage. Here, for using the electricity, we have to decrease the voltage. For both purposes, we require a device. The name of the device is transformer. Now here we understood what is a transformer here. Second thing, principle. It works on mutual induction. Two coils are there. So here magnetic flux will be produced and it will link to the secondary wire. So this works on mutual induction. Yes. Construction, it consists of two sets of coils insulated from each others. So here this is the winding input is given here. This is called the primary winding. Output we get here secondary winding. When alternating voltage is applied to the primary, resulting current produces alternating magnetic flux, and this flux links to the secondary. And EMF is induced in the secondary. Similarly, EMF is also induced in the primary because of this primary winding. This is a voltage applied to the primary S. So we assume transformer is 100% efficient or ideal transformer. So ideal transformer, there are three assumptions. The primary resistance and the current are small. Second assumptions, the same flux links to primary and secondary, same flux. Third, the current in the secondary is small, yes. Now, phi is the flux in each turn in the core at time t. At time t, due to current in the primary when voltage is applied in the primary. So, as per the Faraday's law of electromagnetic inductions, EMF is induced in the secondary is given by Ns d phi upon dt, and this flux depends upon the number of turns in the secondary. Similarly, EMF is also induced into the primary and given by Np d phi upon dt. And here we get the ratio, minus minus is getting cancelled out. Now see, this flux, change of flux at a time t, change of flux at time t, as per the second assumptions, the same flux links both the primary and the secondary. So they are same, that's why they are also getting cancelled out, and here we get S upon EP is equal to Ns upon NPS. Now, as for the third assumptions, the secondary current is small, therefore the losses in the secondary is negligible. So we can say that ES is equal to Vs. So this is ES, and therefore it is Vs, like this one, EP Vp. Similarly, EP is equal to Vp. Replacing here, Es upon EP, Ns upon Np is equal to Vc, Vs upon Vp. So we get one equation here, Ns upon Np is equal to Vs upon Vp. This is the equation number 1. Second, for the ideal transformer, the power in the primary is equal to the power in the secondary. So, power in the primary is equal to the power into secondary. P is equal to Vi. So, here we can write yes, Vp, Ip is equal to Vs, Is. So, from that we will get equation Vs upon Vp is equal to Ip upon Is. This is the equation number 2. So from 1 and 2, Vs upon Vp is equal to Ns upon Np. Vs upon Vp is equal to Ip upon Is. So we can write yes, Ip Is is equal to Vs upon Ns Np. This is the equations of the transformer. Yes. When Ns is greater than Np, then Vs is greater than Vp. In that case, Is is less than Ip. This type of arrangement is called step-up transformer. Step-up transformer, yes. On the other hand, if Ns is less than Np, then Vs is less than Vp. In that case, Is is more than Ips. This type of arrangement called step down transformer. So we will take one example. Here in primary, number of turns are 100. Applied voltage 220 volts and 10 ampere current. Here number of turns in the secondary is 200. We have to find out Is, second current in the secondary, and voltage in the secondary. So we will use this equation. Yes. First find out the secondary voltage. We will use the equation Ns upon Np is equal to Vs upon Vp. Ns is given, yes, 200, 100. We have to find out the voltage in secondary. Voltage in the primary is given, yes, 220 volts. So Vs 220 into 2, 440 volts. So we get, yes, 440 volts. Same current. We will write the equation, yes. Ns upon Np is equal to Ip upon Is. Ns again 200, 100. Ip is given 10 amperes. Is we have to find out. So Is is equal to 10 upon 2. Is is equal to 5 amperes. So we get, yes, 5 ampere current. So here, when number of turns in the primary is 100 and number of turns in the secondary is 200. So voltage 220 volts. So it is increased from 220 volt to 440 volts. Yes. But current, when it is a primary 10 ampere, it is from 10 ampere to decrease to 5 amperes current. Now, all the transformers are not 100% efficient. Some good transformers are there, they are 95% efficient because some losses are there in the transformer. So, we will see the losses in the transformers one by one. First, loss due to flux leakage, due to flux leakage, yes. The reason is due to due to poor design of the core or air gap in the core. Minimized by winding the primary and secondary one over the other. Let us see in details. The primary winding, when alternating voltage applied to the primary, resulting current produces alternating magnetic flux, yes, and all the flux produced here should reach to the secondary. But due to the poor design of the core or air gap in the core, if there is some air gap, so from this air gap some flux, magnetic flux returns to the primary. Instead of reaching this flux, all the flux to the secondary and links here, but some flux is out, some leakage is there, and due to this it comes back to the primary, and due to this less EMF is induced here. So it can be minimizing by the primary and the secondary one over the other CS. Now this is the coil. This is the coil, and so primary and this is the secondary winding one over the others, and they are insulated from each other, yes. So this is the coil and the laminations are put in this one. This is the laminations. Like this one. So here is the laminations, and this is the central limb. This is the central limb here, and both the windings are on the central limb. So here this winding is there, and over there is another winding, and central limb will be inside here like this one. So this can be minimized by winding the primary and secondary one over the others. Second loss, due to resistance of the winding wire. Loss due to I square R. So winding wire has some resistance, and you know that as per this formula I square R, if resistance is more, I square R loss is more, and the energy is spent in the form of heat. So it is a wasted. So can be minimized. Can be minimized by using thick wire to high current low voltage winding. primary and secondary. Where the current is more, so that time voltage will be less. So in this winding, use the thick wire for this winding. Yes, we know that resistance is inversely proportional to the cross sectional area. This is the one wire whose cross sectional area like this one. Another wire whose cross sectional area is more than the first wire. Yes, if you are using this wire, its cross sectional area is what? Less than this one. So if the cross sectional area is less, R will be more. If R will be more, again I square R loss will be more. Yes, and so heat energy will be wasted in the form of heat. Yes, if you use this wire, thick wire, cross section area is more, cross section area is more, resistance will be less, I square R loss will be less. Yes, third loss, eddy current. Due to eddy current, alternating magnetic flux induces eddy current, and resulting expenditure of energy is in the form of or simply we can write yes, eddy current causes alternating magnetic flux induces eddy current, and this causes heating. Yes, this loss can be minimized by having laminated board. So here you know that eddy current, so any magnetic field lines are there. If a metal is come in contact in this magnetic field, so here in this metal eddy current will be induced due to change of the magnetic flux. Yes, so same here in the core, this is the core here. If it was a core here of one metal, so here eddies will be formed, eddy current will be induced because there is what? Alternating magnetic flux is there. If alternating magnetic flux is there in the core, eddy current will be induced, and because of this it will be produced here in this core here. So what we are using here, instead of one metals, so we are using the laminations. These are the laminations, and we are combining all these laminations, a core is made like this one. Now again, these laminations are insulated from each others. They are insulated from each others. So no current can pass from this one. Even the eddy currents are induced here, this eddy current cannot pass from one laminations to the another laminations. So this is the can be minimized by having a laminated core. This is the core. This is the core made by this laminations. Yes. And the last one, hysteresis. Fourth one, the magnetization of the core is repeatedly reversed and resulting expenditure of the energy appears as heat. It can be minimized by using a magnetic material which has low hysteresis loss. This is the hysteresis curve. Due to this alternating current, alternating magnetic field is produced here, and in the first cycle this curve is like this one. So it gets saturated, again demagnetized, and again in the next half cycle, which is a negative, it is again magnetized in this one. So in this way, the magnetizations of the core is repeatedly reversed. Means this is the ferromagnetic materials. If in the first cycle magnetic field is in directions, now in the material, ferromagnetic material, magnetic dipoles are there or domains. They align with the magnetic field. In this half cycle, first half cycle, when this is in directions, the magnetic field is directions, so this domain magnetic dipole, they will also align with the magnetic field. Yes. In the next half cycle, the magnetizations will be reversed and the magnetic field is in this direction. So these magnetic dipoles or domains, they also change their directions, and this repeatedly occurs. Plus minus, plus minus, plus minus, plus minus. So this is the magnetizations of the core is repeatedly reversed, and there is what in this process, there is a frictions between the magnetic dipoles or domains, and due to these frictions, resulting expenditure of energy appears as heat. So it can be minimized by using a magnetic material. This is the materials which has a low hysteresis loss. So if this curve is less, material which curve is less, so loss will be less. Yes. So in this way we can minimize the loss due to hysteresis. So with this we complete our topic alternating current years. So students, exams are around the corners and you are busy in your studies. So this was my small effort and I hope this will be useful in your studies. So thank you very much students for watching this video. Have a good day.